2, 1. Okay, welcome to the pre-recorded lecture for the 17th of February. I'm going to go for this one a little quick. I'm feeling a little congested under the weather. So, last time we talked about the dot product. Today we will finish up talking about the triangle inequality. We sort of set up a goal once we established dot product and saw some of the geometric interpretations of it. So our goal is to prove that. We will then address the situation when things go from real to the complex case, and then we'll wrap things up by introducing the notion of orthogonality in Rn. Alright, so given two elements of Rn, their dot product is defined as follows. You match up their components, you multiply them, and you add them up. As we mentioned, kind of at first glance, this is like a valid computation, but it's not exactly clear why you would ever exactly want to do this. Though we did note that, hey, these suspiciously look like the components of a system of linear equations, so maybe there's a connection. Alright, but before we get to that, we did note that there is a geometric tool present, because if you dot product an element of itself, you have a non-negative quantity, and thus you could take its square root. And we noted that if you look at this in R2 specifically, it's the square root of a squared plus b squared. Good old Pythagorean theorem. Alright, so we then obviously said, well, clearly we have this picture we can draw in R2, but there's nothing stopping us from defining it for R3, R4, up to R837, whatever you want. Alright, so that's our notion of length in Rn, and we established some pretty basic facts of this, and we note that these facts followed the intuition of what a length should be. It's a non-negative quantity, a length of 0 precisely if you have the 0 vector. Scaling scales the length accordingly. And then we said, well, if you draw two vectors in R2, the length of their sum is the length of the diagonal of the parallelogram, so that should be less than or equal to the sum of the individual lengths. And that's the triangle inequality, but we noted that it's not immediately obvious how to prove that from this direct formula. So first, as we discovered, when you prove that this formula holds, we discover that it's better to work with the norm squared rather than the norm, because once it's squared, you remove the square root, and then you can rely on the algebraic properties of dot products. And that gave us this beautiful little formula here. This ends up being sort of like the thing. You can get away with a lot of theorems with this, and one of them that you can get away with is something called the Cauchy-Schwarz inequality, which states that the absolute value of a dot product does not exceed the product of the norms. Okay. And note that absolute values are always greater than the actual number itself, so this also implies that the dot product itself does not exceed the product of the norms. Alright, and equipped with that, we can then finally establish our good friend, the triangle inequality. So as we claim, the sum of a length, the length of a sum is less than or equal to the sum of the lengths. Right, and you prove this by squaring this, giving you this, then noting that this component here is less than that, and that this whole thing here is the sum of the lengths quantity squared, square rooting both sides, finishing up the proof. Hey, there you go. Alright, so all of this went super well and great and wonderful, but note, again, we were using real numbers for everything, and as we've mentioned, we're going to have to dip our toes into the complex plane here and there as we go through the course, so natural question to ask now is what happens with complex numbers. Okay, so you can take their dot product, nothing's stopping you, right? You can make this computation, but there's an issue now with this computation. It's possible that you can dot product a element with itself in Cn and arrive at negative real numbers. And again, that's not surprising. There are complex numbers that square to -1. So dot products which are built off of multiplication, there is summation, but they're right at the heart. There's a product occurring. We know we can square complex numbers and go negative, so it's not shocking that the non-negativeness of dot products is no longer a thing for the complex case. Now, to correct it, what you can do is define the inner product of two elements in Cn to be the following. So instead of the dot product notation, we use this bracket notation. And note that now the change in our computation is the conjugation of the second component. Okay. Now, at first glance, this might seem, again, mildly artificial, right? Again, this is a valid collection of math symbols. Great, we can do this. But as we're going to see here, as we list out some facts, that ends up being the correct modification to get a notion of a product in Cn that behaves basically how dot product does. Okay. So, let's list off the facts of inner products. We're not going to prove any of these, and I'll just note that their proofs are basically the proofs we saw for dot products. You just need to be aware of the conjugation occurring on the second component. Okay, so first off, inner producting an element with itself indeed gives you a non-negative real number that only hits 0 if you have the 0 vector, and that comes from the fact that if you inner product an element with itself, you'll get the sum of the modulus squared. And again, that's coming from the fact that a complex number times its conjugate gives you its modulus squared. So the non-negative quantity, the positive definiteness, if you will, of inner product is of the dot product now carries over to the inner product. Note we lose the symmetry. Sort of. We still have it, but then you have to be mindful of the conjugation on the second component. So you don't have full symmetry. What you have is what's known as conjugate symmetry. Now, note that doesn't affect the addition, distributivity. The sum of elements and then inner product will distribute accordingly, the same way dot products do. However, with scaling, while you can pull a scalar out of the first component, no problem, when you try to pull a scalar out of the second component, you actually pick up its conjugate. Now, for real numbers, we don't care, because conjugating a real number doesn't do anything, but for complex numbers, this actually, this causes some interesting things to occur, and like I said, again, we're not going to be obsessed with the complex plane, but every so often we'll hang out in there and see something, and we'll see some interesting consequences here. Alright, and now with this upgraded version of dot product for Cn, which then gives us the 5 axioms that we saw dot products have, more or less, you can then extend the definition of norms from Rn to Cn by, again, just taking the square root of the inner product. And all of the previous facts about norms that we established are going to remain true, but there is one huge exception. This result right here changes ever so slightly because of the conjugate symmetry. Now note in the proof of this, right, we had x dotted with y plus y dotted with x. Well, then with inner products, you'd have inner product of zw plus inner product of wz. And so when you swap it, you won't pick up twice the inner product, you'll rather get twice the real part. So everything that we proved before about norms remains true, but now you'll just pick up this real part and just got to keep that in mind. Okay. The triangle inequality and the Cauchy-Schwarz inequality still hold true as normal, but this result here, a real part appears. Again, the consequences thereof are mildly interesting, but again, we're not going to get so deep in the world of complexes. Okay. Alright, so now that we've done that, let's hit the last point for today, orthogonality. Alright, let's start off with a picture. Alright, so I made reference to this. Note that if you draw out this triangle, you get the good old law of cosine. C squared is equal to a squared plus b squared minus 2ab cosine of the angle. Right, so note this is the generalized version of the Pythagorean theorem. Right, if you have a beautiful right angle there, the cosine drops out, because you'll have cosine of pi over 2, which is equal to 0. And you get a squared plus b squared equals c squared. But, following what we were just discussing with this particular formula for the dot product case, if we let A be the length of a vector x and B be the length of a vector y, then C ends up being the length of their difference, and replacing the plus with a minus changes the plus here in the twice the dot product part. You can verify that computation. And then matching this formula to this one reveals that the dot product of x and y is the product of the length of x and y times cosine of the angle. And note that that kind of pops out of the Cauchy-Schwarz inequality, because this establishes that the dot product is somewhere between the product of the norms and the negative of the product of the norms, meaning that there's some cosine factor that gets them to line up. All right. And indeed, note here that if cosine, if the angle is pi over 2, then the cosine is 0, meaning the dot product would equal 0. So in light of that, we'll define a list of elements to be orthogonal if their dot products are equal to 0 when their indices are different. Okay, so unpack that again. A list of elements is said to be orthogonal if their mutual dot products are 0 when the indices are not the same. Note you need this indices are not the same because if you required all possible dot products to equal 0, well then vk dot with vk would equal 0, but as we know that would then force vk to equal 0. So the only things that could be orthogonal are a list of zeros, which we don't want that. Okay, and again, it's worth noting that for elements of Cn, the dot product here must be replaced with the inner product to keep the non-negative quantities that dot product possesses in Rn. All right, let's wrap up today with a proof. So we're going to prove something about orthogonal things. This will get us a feel for how proofs with this concept is going to go. Sorry. And what we're going to prove is basically the beefed up version of the Pythagorean theorem. Now, the Pythagorean theorem says that if you got a big old right angle here with theta, then a squared plus b squared is c squared. Well, it turns out that for Rn, you can get a Pythagorean theorem for any number of elements and any scalars that you associate with them, where the length squared of the sum is equal to the sum of the length squared, and then the appropriate scalars being squared as well. All right, and this is again, straight unravel the definition. If you look at the norm squared, you'll then have the dot product of the element with itself. Now, note here the trick I'm pulling. I have sigma notation with my summations, and the k here, again, is a dummy variable, right? This doesn't mean anything. You just need a symbol to indicate that we're going to start with 1 and go up to m. So I can use k with the first one and j with the second, no problem. Now what am I going to pull? Well, now I'm going to note that dot products distribute and pull out scalars, so all of these alpha k's can be pulled out, and all of the sums can be pulled out, no problem. And then I'll pull that same move again in the second coordinate. These scalars can be pulled out, and these sums can be pulled out. And then we have these dot products here, and then by definition of orthogonality, those dot products zero out whenever the indices are different. And when the indices are the same, you'll get the length quantity squared, by definition. So in this summation here, everything drops out except for an alpha k, then length of vk quantity squared. Just like that, and there you go. What was to be proven has indeed been proven. And there we go. All right, cool. Okay, there we go. Proven a little fact about orthogonality. So we've introduced this new notion of orthogonality, and with that we've proven a beefed up version of the Pythagorean theorem. Okay. Alright, so next time we'll investigate orthogonality's role in linear independence. We'll look at some more explicit examples of things that are orthogonal and are not orthogonal. The kids are going nuts, so I gotta go deal with them, and I'll see you in person tomorrow.